Okay, so in this video, we're going to talk about Dalton's law of partial pressure. Okay, so we frequently deal with mixture of gases instead of pure gases. In the atmosphere, we have nitrogen, oxygen, argon, and carbon dioxide, right? So as you can see, nitrogen is the most abundant in the atmosphere. So the gas laws still apply to mixture, okay, not just pure gases. Since gases mix homogeneously, the total pressure exerted by a mixture of gases is the sum of the partial pressure exerted by each individual gas in the mixture. So let's talk about law of partial pressure. This is discovered by John Dalton in 1801. For any pure gas, PV-nRT holds true. Okay, so therefore, pressure is directly proportional to N, or the amount of gas, if volume and temperature remain constant. So meaning, as N goes up, so would P, or the reverse. Okay, so let's take for example neon. If the amount of gas or neon doubles, the gas pressure of neon doubles. So Dalton's law immediately follows from this example, since each gas is causing 50% of the pressure. Okay, so meaning if helium is added instead of another neon, gas pressure doubles. So summing their two pressure gives the total pressure. We can have this equation, pressure of neon plus pressure of helium will give us the total pressure. Okay, this is what Dalton's law of partial pressure says. So each gas in a mixture creates pressure as if the other gases were not present. Okay, so the total pressure is the sum of pressures created by the gases in the mixture. The formula will be P total is equal to P1, P2, P3 plus Pn. So 1, 2, 3 stands for any gas present in the mixture, and N is the total number of gases in the mixture.
I don't understand. I don't understand, bitch. I don't understand. I don't understand, bitch.
Remember, the only thing that you need here is that the two gases do not interact in some chemical fashion, such as reacting with each other. Okay? The pressure of each gas exerts in a mixture is called partial pressure. So another concept that is related to partial pressure is the mole fractions.
What is happening? Is everything okay?
So the concentration of each component in a mixture can be expressed as a mole fraction, X, which is the number of moles of the component divided by the total number of moles in the mixture. So to make it clearer, let's have this equation. This means that XA, mole fraction of gas A, is equal to the number of moles of gas A over the total number of moles present in the mixture. It's the same as B. So, in a mixture of gas, the mole fraction of each gas is the same as the ratio of the partial pressure of the gas to the total pressure. With that, mole fraction of A is equal to the partial pressure of A over the total pressure of gases in the mixture. And to solve for the partial pressure of A, just manipulate the formula. This will give us mole fraction of A times the total pressure. So to make it clearer, or to give you a view on how to use this, let's have a problem.
I understand your concern, but I do not have the same concern.
Okay.
A container holds three gases, oxygen, carbon dioxide, and helium. The partial pressures of the three gases are 2 atmospheres, 3 atmospheres, and 4 atmospheres, respectively. What is the total pressure inside a container? I have this diagram. So 3 containers containing each gas. Okay, and the formula here is P total is equal to PA plus PB plus PC. So applying the given, P total is equal to the partial pressure of oxygen plus the partial pressure of CO2 plus the partial pressure of helium. Now just insert all the given. So the P total is 2 atm plus 3 atm plus 4 atm, and the answer will be 9.00 atmospheres.
Very good.
Okay, it's just so easy, right? Now let's have a more challenging example.
No, no more. Stop here.
A mixture of gases contains 2.14 grams of nitrogen, 5.85 grams of hydrogen, and 4.18 grams of ammonia. If the total pressure of the mixture is 4.58 atmospheres, what is the partial pressure of each component? So for this problem, we are asked to get the partial pressure of each component, not the total pressure. So since we're dealing with the number of moles and we're given the number of grams, we have to convert this to moles. Okay, so the first step will be to determine the moles of each gas. If you're not familiar with how to do this, watch the previous video about mole conversion. Using the molar mass of nitrogen gas, this will give us 0.07639 moles. Hydrogen will have 5.80357 moles, and ammonia will have 0.245435 moles. Now you have to add them up to get the total number of moles. This will give us 6.125435 moles. Okay, so as you can see, I'm still not rounding off. Now divide each mole by the total moles. Okay, so we will have this. The moles of nitrogen divided by the total number of moles. That will give us 0.01248. For hydrogen, 0.94745. And ammonia, 0.04007. The next step is to multiply the mole fraction of each gas times the total pressure. Okay, so remember, PA is equal to XA and times P total. So we're going to use this. But this time, substitute A with nitrogen, hydrogen, and ammonia. So doing this, for nitrogen, this will give us the equation 4.58 atmosphere times 0.01248. This will give us 0.0572. So where did 4.58 come from? It's here, the total pressure. Okay. So just do the same with the other gases. And that's it. You have the partial pressure of each component.
Hoy, ang bilis nyo naman. Excited? Hindi naman kayo nagpaawat, guys.